So we are going to review our linked list. During your programming too, you already encountered linked lists. However, because of the pandemic, it was not explained to you thoroughly. So we are going to revisit again our linked list in this lesson. So linked list, the first thing to know when we encounter linked list is that we should know the concepts of nodes. So the concept of node is that a node is an object. A node is an object. And this node object contains at least two elements. One is a pointer element, wherein in this figure, we named it as next, and then the other element is the data element. In this figure, we named it data. There are nodes that contains a single element, like for example, this head. And this head is only a pointer element. Let's try to compare linked list with array. So this image is a typical graphical representation of a linked list. And for an array, this is the typical graphical representation of an array. So let us examine both. So this linked list and array both contain the same data elements. So in this linked list, we have a data element of 1, 2, 3. Its counterpart on an array is like this. Data element 1 at index 0, data element 2 at index 1, data element 3 at index 2. In accessing our arrays, we only need our index. So for example, if I want to access the data element 2 in my array, I would only issue a code like this. Example, my variable name for my array is R, and then I would only access index 1 to get the value of 2. For my linked list, how will I be able to access the value 2 in my linked list? So, is it node that data? No, it's not node that data. The conceptual way of accessing the data element 2 in this linked list is head dot next dot data. So head dot next dot data to access data element 2. In reality, the way to do that through code is we're going to loop through our linked list. We need to loop through our linked list while we are not yet on that node wherein the data element resides, we will still continue to loop. The difference of the complexities of accessing data elements for linked lists and arrays is obvious. For arrays, it's order of 1 constant because we are only issuing linear code. However, for a linked list, again, we're going to loop through our linked list until we reach the node that contains that data element. So if we're going to loop through all data elements or n, then the complexity is order of n. So in accessing data elements, the obvious winner is the array data structure. But there are advantages of linked lists over arrays. You can read those on our LMS learning material. Like for example, linked list is a dynamic data structure. So we can just add nodes or data dynamically. Wherein for array, we cannot do that. Once we instantiate an array with values, in this example, the size of this array is already 3. It has 1, 2, 3. We cannot just add another memory space in our array. We need to declare again another array with a larger specific size, and then we transpose the values of this array to that array that we are going to newly instantiate. So on that note, linked list is more advantageous than array. We can access the operations or methods of linked lists using java.util.linked-list. And you can check all of those operations or methods on the Java documentation. However, for our learning tasks, we would like to restructure the codes for the class of linked list for us to be able to understand the complexities of the operations of linked lists. So in this code, let us read it line by line. Public class linked list. I named my class linked list, and then I have less than symbol e, greater than symbol. This one is called a generic. You will learn generic on your object-oriented programming. I would only like for you to understand that this generic can accept any data type or object. And then this linked list class implements list I. So list I is also a user-defined interface. So you can check on our learning tasks the code for our list I. And this list I also accepts parameter that is generic, any data type or object. And then the following code is our object signatures and constructor. First is our class for node. So let me read class node E, and then E data, node E next, and then we have the constructor for the node, which is public node with parameter data type E with name object, and the code for that is data is equal to object, next is equal to null. In our tester class, if you are going to issue a statement like this, node E node is equal to node E object, this code will trigger the constructor. This code will trigger the constructor for class node. So whatever we pass in this object, whatever we pass with this object, if it's an integer, for example, that integer value will be read by our class. This E will become integer. So this E will become integer also. This E will become an integer also. And of course, in our constructor, our E here will be changed into an integer, and then our object, for example, the value itself will be the integer, and then that value will be the value of our data element. And our next variable will point to null. So our equal sign denotes that we are pointing to null. So once we issue this code, node E, node is equal to new node E, and then the value of the object, then the graphical representation of this is that we will be creating a node with a next element, next pointer element pointing to null, because we have this code in our constructor, and then our data element will be equal to our object, whatever that is. So for example, if it's an integer, for example, I passed 1 here, then this object will also be 1. So data is equal to 1, for example. So that's the class for our node object. Every time we are going to create a node, this is our code. Next, private node E head, private int current size. So this private node E head, we're going to create this graphical representation. We're going to create a node that only has a pointer element. Okay? And then private int current size. Private int current size is a variable to track the size of our linked list. Next is our linked list constructor. So a constructor contains this code: public linked list, open and close parenthesis. And the statements within the constructor is head is equal to null, current size is equal to 0. In my tester class, if I issue this code list I, and then my parameter is an integer, list is equal to new linked list, integer, open and close parenthesis, colon, then the linked list constructor will be triggered. The linked list constructor will be triggered. And the graphical representation of that is this. Our head node is pointing to null because we have this code. Head is equal to null. Our head will be pointing to null. And our current size will be initialized to the value of 0. Once again, when we're going to instantiate our node object, this will be the graphical representation of it. And it is based on the statements on our constructor, on our node constructor. If we're going to instantiate the object list, our graphical representation would be like this. And it is based on the constructor for our linked list. Our linked list class, based on our Java documentation, has numerous operations. So we're going to examine the basic operations for a linked list. And the first one is this. addFirst. addFirst. Let me just read the code. Public void addFirst, wherein it takes a parameter with a type E and the name object, obj. And then the statements within this function is node E, node is equal to new node E, and then object, and then node.next is equal to head, head is equal to node, current size plus plus, and then that's the end of the statement for our addFirst. So let's check the process of addFirst. If my linked list is empty, let's check this code in tester class. So my code for tester class is this: list I integer list is equal to new linked list integer, open and close parenthesis, semicolon. And then after this instantiation of the list object is I issued list.addFirst with 1 as my data parameter. So this is my code for my tester class, and I would like to see the graphical representation of how this is being done. So let us follow. The instantiation of my list object triggers this. The creation of the head node pointer pointing to null. And then the second line of code here, list.addFirst triggers this function. And then the first line of code, node E node is equal to node E object, triggers the constructor for our node, and it creates this graphical representation. So 1 is passed here in our object name, and then that 1 is also passed here, and that value 1 is passed as a parameter for our node, for our data element for node. That is why the final graphical representation in the instantiation of a node is this. Node next pointer is pointing to null, and then the data element is now equal to 1. So that's how we do this line of code. Next, our number 2. It says here node.next is equal to head. So in this newly created node, node.next is pointing to null. We want the value of head for our node.next. So head here is pointing also to null. So this means that our node.next should be pointing to null. So in this number 2, head now is pointing to null, and our node is also pointing to the same null where head is pointing. Okay? And then number 3 of our code, head is equal to node. Head is equal to node. We want head to point to our node. We want head to point to our node. So head is now pointing to node instead of head pointing to null. So head pointing to node, while our node.next still points to null. So this is our graphical representation until step 3. And then our step 4 is current size plus plus. So current size is 0 initially based on our constructor of our linked list. Constructor of our linked list. Now it becomes 1 because we already added our node and it's already properly linked. It's already properly linked. How about if my linked list is not empty? If my linked list contains already an element, like let's take this for example. I have one node in my linked list. So this is the additional code in our tester class. I would like to issue another addFirst list.addFirst with parameter value of 2. So initially the graphical representation is this. We take this example, we just transpose it here. So let's run through again our addFirst. 2 is passed to our object, and since it is an integer, our e here will be an integer. So this value 2 will now be transposed here in our object parameter for node, and the constructor for node will do the rest. And this is the graphical representation of step 1. So it will also create a node with next pointing to null, and the data is now equal to 2. So that's how number 1 is being done. Next, number 2. Node.next is equal to head. We want our node.next to point where head is pointing. We want our node.next to point where our head is pointing. So our head is pointing to our previously added node with data element 1. So in our number 2 step, this is how it is represented. Our new node is now pointing to what head is pointing, to the previous added node. Okay? And then our number 3, head is equal to node. We want head now to point to the newly created node. We want our head to point to our newly created node. Instead of our head pointing to the previously created node, we want our head to point to the newly created node. So our number 3 step, final graphical representation, is this. Head pointing to node with data element 2, and that node that next pointing to the previously created node with data element 1, and this node that next pointing to null. So this is the final graphical representation. Examining the code for our addFirst. The complexity of this line of code is 1, 1, 1, 1. Hence, addFirst complexity is order of 1. How about another operation called addLast? So we want to add at the end of our linked list, not at the beginning of our linked list. So this, for example, is the code for my addLast. And I have already noted here that the complexity of this code is order of n. Order of n. Because in my code, I have a while loop. Once I have a while loop that will loop through all of my n, then the complexity is already order of n. So let's examine my code for addLast. So the first is the instantiation of an object node, because I'm adding, of course. And then the second line of code is the instantiation of a node TMP, wherein the value of TMP is the value where head is pointing. I have a conditional statement. If head is equal to null, then I will do the following statements. Head is equal to node, current size plus plus, and then return. Outside that conditional statement, I have a while loop. So my while loop contains a condition, tmp.next is not equal to null. So while tmp.next is not equal to null, I will do the following statement. tmp is equal to tmp.next. Once the condition is already false, I will exit this while loop, and I will do tmp.next is equal to node, current size plus plus, and that's the end of my code for addLast. Let's examine how this operation is done. So if I have an empty linked list and I issued the following code in my tester class, list I integer list is equal to new linked list integer, and then list dot addLast, and then I'm passing 1 as a parameter of my addLast method. So this is the graphical representation. So A, the instantiation of the list object triggers the constructor, and the constructor creates the head node pointer pointing to null. Okay? And then we'll now go to our list.addLast with the value 1 passed as parameter. So this one will go through here. Since it is an integer, this e will become an integer type, and that value will be stored to the object name obj. And this one will be our parameter for our node object, to our newly instantiated node object. Okay, so this is how it's graphically represented, just like the previous. That's step 1. So step 2, the node TMP will be pointing to head. So head currently is pointing to null. So we want our node TMP to point also to null. So there, it's already pointing to null. And then we're going to do the if statement. If head is equal to null, if head is equal to null, if head is pointing to null, then we are going to do these statements 3 until 5. Head is equal to null because currently head is pointing to null. So we're going to do number 3, step number 3. So step number 3, head is equal to node. Our node is this, the newly created node. We want our head to point to our newly created node. So head now will be pointing to node and not pointing to null anymore. So we will be removing the link of head to null. So this is the graphical representation for until step number 3. We want to increment our variable current size because of this statement, current size plus plus. So this is it, or current size initially 0, instantiated on our constructor for our linked list, and now it will become 1. Okay, and then number 5, return. So once we have this code, we will now go outside our function. We will now go outside our function and we will not do the rest of our codes. Okay? So there it is. Get out of the function. Now, the final look of our linked list is this. What if my linked list is not empty? If it has already a content. So I want to add additional code in my tester class. Aside from the addLast before, I would like to also add again using this code list.addLast with parameter 2 value. So the graphical representation of this is here, and we will do it step by step. So once I pass 2 value to my addLast method, it will go here, and that 2 will be read as an integer. That 2 will be passed here, and that 2 will be passed to our node object, our newly created node object on step 1. Okay, so in step 1, this is the graphical representation of that. A newly created node with next pointer pointing to null, and the data is equal to 2 already. Okay, and then step 2, node eTemp is equal to head. So my TMP will be pointing to what head is pointing. So initially, Since our final uh, graphical representation of our linked list before is this, head is pointing to our node. So we would like TMP to also point to what head is pointing. So TMP will be pointing to node also. Okay. Let's test our if statement. If head is equal to null, if head is equal to null, head is equal to node. So this is false, meaning we are not going to do this statements within our conditional statement. We will go outside and go directly to our while loop. So while tmp.next is not equal to null, we're going to do this line of code. So let's test. While tmp.next is not equal to null, we're going to do tmp is equal to tmp.next. But my tmp.next is already equal to null, meaning we will not do our while statement. We will go out of our while statement because it is already false at our first attempt. Okay, so we will go outside our while loop. We will go outside our while loop and do our step number 7. So tmp.next is equal to node. Our tmp.next, we would like to point that to our newly created node. Our tmp.next, we would like to point that to our newly created node, which is like this. So our step number 7, the final look of our linked list will be like this. Our tmp.next with that node data element equal to 1 will now point, our tmp.next will now point to the newly created node. And then number 8, current size plus plus. Current size plus plus. So our current size is 1. Now it will become 2. Let's examine the complexity of this line of code, although it's already written as our comment as complexity order of n. So this line of code is 1. Line of code is 1, 1, 1, 1. This for loop, this while loop is n. It's 1, 1, 1. So applying the rules of algorithm analysis, the final complexity is order of n. Can this line of code be improved? The answer is yes. And it's up to you to find out how to improve our code for addLast and turn it to just order of 1. And we can do that by implementing our tail node. Another operation for linked list is our removeFirst. So our removeFirst code is like this. We have a conditional statement. If head is equal to null, then return null. And then we will be declaring a temporary variable of type e equals to head.data. If head is equal to tail, head is equal to tail is equal to null. So this is the shortcut for head is equal to null and tail is equal to null. Else, head is equal to head.next, current size minus minus, and return temporary. Let's examine this function removeFirst. If my linked list is empty, and then I have this code for my tester class, list I integer list is equal to new linked list integer, and then I have list dot removeFirst. This is my graphical representation. So first, letter A step, we are instantiating the list object. So previously, our head is pointing to null, but why is this like this? Tail is also pointing to null. In this code of my removeFirst, I already implemented the tail node. So let us go back to our node object signatures and constructor and our linked list constructor. If I'm going to implement tail node, then I would add here tail. And also I would initialize the value of tail in my linked list constructor. So if this code is issued, then my tail will now also be pointing to null. So that is why for my code, for my removeFirst, letter A is already represented as this. Okay? After that, instantiation of the list object, list.removeFirst. So you can notice that I did not pass a parameter in my method removeFirst. However, the removeFirst function in my linked list class has a signature of E. So whatever is the data type of my linked list elements, it should be returned also. Okay. So let's run through our removeFirst. If head is equal to null, then return null. So in this conditional statement, it is true because head is equal to null. Head is pointing to null. So we will get out of the function and return null already. So once we have returned null here, we will not be doing the rest of the codes. We will get out of the function and we will return null. But that's for empty linked list. If my linked list contains a single node, okay, if I have a linked list with one content, then I would like to add additional code for my tester class. So list.addFirst 1 and then list.removeFirst. Okay, so list.addFirst graphical representation is this. Okay, head will be pointing to our node, and then tail is also pointing to the node, and node.next is pointing to null. Okay, let's run through our removeFirst function. If head is equal to null, head is equal to node in this case. So it's false. We will skip this step. We're going to go to a step number 2. E temporary is equal to head.data. Our head.data is 1. So head.data will be stored in our temporary variable. Okay, so that is this. 1 is stored in variable named temporary. So E here is, of course, integer because the value is 1. If head is equal to tail, then we're going to do this. Head is equal to null, tail is equal to null. So in this case, head is equal to tail because they are pointing to the same node. Okay? Head is equal to tail. That is why number 3 is illustrated like this. Head now will be pointing to null and tail will be pointing to null also. And then we decrement our current size. So current size minus minus, since it is 1 before, it will now become 0. And we will return temporary. We will return 1, the data element 1, here. We will return our temporary with data element 1 here. What if my linked list contains more than one node? So, example, I have 2 nodes on my linked list and I want to issue removeFirst. So I would like to add additional code for my tester class. For example, list.addFirst1, list.addFirst2, and then I would like to issue list.removeFirst. So doing list.addFirst1 and list.addFirst2 will have this graphical representation. Head is pointing to node with data element 2. Node.next is pointing to node with data element 1. Node.next is pointing to null. And our tail is pointing to our node with data element 1. Now we're going to do removeFirst. Let's examine our code. If head is equal to null, head is pointing to this node. So it's not equal to null, so false. We're going to go to step 2. E temporary is equal to head.data. So 2, since removeFirst, this one, 2 is stored in variable named temporary. Okay? And then we're going to go to our conditional statement. If head is equal to tail, if head is equal to tail, head is still pointing to our node. Tail is pointing to the node here. So it's not equal. False. We're going to do else statement. Head is equal to head.next. So our head.next is this node. So our head will now be pointing to this node. Okay? Head.next is this one. So our head will now be pointing to this one instead of this. So number 4, this graphical representation is like this. Head is now pointing to the node with data element 1. And then our tail is pointing to this node. The node.next is pointing to null. Our node with data element 2 is still pointing to our node with data element 1. Okay? And then, after that, current size minus minus. So from 2, it will now become 1. And then return temporary. So we are going to get out of the function and return the value of temporary, which has the value of 2. So this is the look of our linked list. The final look is only this one. Okay? Because this node, although its node.next is pointing to this node, no one is pointing to it. No one is pointing to it. Once that is read by our compiler, and our virtual machine will garbage collect it. Okay, so once it is garbage collected, it is similar to being deleted. Okay, so this will be deleted. This will be deleted. And then the final look of our linked list is this. Again, if no one is pointing to a node with a pointer element and a data element, it will be garbage collected by our Java virtual machine. Okay? Let's examine the complexity of my removeFirst code. So return null 1, temporary is equal to the data 1, 1, 1, 1, 1. So the final complexity is order of 1. Okay? How about the operation removeLast? I want to remove the node at the end of my linked list. Okay, so here is my code. If head is equal to null, return null. If head is equal to tail, return removeFirst. Then node eCurrent is equal to head, previous is equal to null. While current is not equal to tail, previous is equal to current. Current is equal to current.next. Previous.next is equal to null. Tail is equal to previous. Current size minus minus. Return current.data. Okay. I would like to test my removeLast function. So if linked list is empty and I have this code for my tester class, this I integer list is equal to new linked list integer open and close parenthesis semicolon list.removeLast. This is the graphical representation. Okay, so letter A, the instantiation of my object list will have this output, head pointing to null, tail is equal to null based on our constructor. So that's it. And then removeLast. Okay, let's run through our removeLast codes. If head is equal to null, it's true because head is pointing to null. Return null. Okay, return null. Once we have the return here, return keyword, we will not do the rest of the codes. We will go outside, so that get out of the function and return null. Okay, if my linked list has a single node, a single content, so I would like to add additional code for my tester class. I have addLast with 1 and then list removeLast. Okay, but this is the graphical representation of addLast. This one, head is pointing to node with data element 1. Tail is also pointing to that node, and node.next is pointing to null. Well, let's examine the code of removeLast. If head is equal to null, head is equal to node, so this is false. Let's go to here. If head is equal to tail, head is pointing to node, tail is also pointing to node, so this is true. We're going to do return removeFirst. So we're issuing a method removeFirst. We will do removeFirst. Okay, we will go back here and we were going to do removeFirst. So if that is a single node. That is a single node. Then we're going to do this line of code. This one, right? Head is equal to tail at 1, and then the final loop is like this. Head and tail pointing to null. Okay? So that. Return remove first, this number 2. 1 is stored in variable named temporary. Okay? Since we are going to do remove first, and we also have this, it will return temporary. Okay? Once we have returned keyword, we'll go outside removeLast. And then finally, if my linked list has more than one node, okay? My linked list has more than one node. I have additional code for my tester class like this. List.addLast1, list.addLast2, and then list.removeLast. So, list.addLast1 and list.addLast2 has a graphical representation of like this. Head is pointing to node with data element 1. Node.next is pointing to node with data element 2. Tail is also pointing to this node. And then node.next is pointing to null. Okay? Then we issue removeLast. If head is equal to null, false, because head is pointing here to this node. If head is equal to tail, false, because tail is pointing to this node. We're going to do step 3. So we are going to declare a variable current and instantiate it with head. Declare a variable previous. Declare a node previous and instantiate it with null. So that is illustrated using this. So current is equal to head. So head is pointing to this node, then current is also pointing to this node. And then previous is pointing to null. Okay? I have a while statement. While current is not equal to tail, I will do step 4 and 5. Okay? While current is not equal to tail, tail here is pointing to node with data element 2. Current is still pointing here. So, while current is not equal to tail, we are going to do step 4 and 5. So, current is not equal to tail. That's true in this case. We're going to do step 4. Step 4 is previous is equal to current. So, previous equal to current. Current is pointing to this node, so previous will also be pointing now to this node. That's step 4. So, it's depicted here. It's depicted here. And then, current is equal to current.next. So, current is equal to current.next. Current.next is this node. So, we want now current to point to this node. So, it's depicted in this. Current is now pointing to the node with data element 2. So, okay. Let's go out to that first iteration of the loop. While current is not equal to tail. So, now, on the first iteration of the while loop, current is here, pointing to this node. But tail is also pointing to this node, so this is now false. Okay? Once it's false, we're going to go to step 6. Step 6 is previous.next is equal to null. So, previous.next, we want it to be equal to null. Previous.next equal to null. Okay? So, that is depicted here. previous.next is equal to null. Okay? And then we want tail is equal to previous. Tail, currently here, pointing to this node with data element 2, will be pointing to what previous is pointing. So previous is pointing to node with data element 1. We want it here. We want it here. So it is represented here. Tail, number 7. Okay. And then number 8, current size minus minus. Current size is 2. Will now become 1. Return current.data. Okay. So number 9, get out of the function and return value of temporary, which is 2. So let us just examine the illustration of our linked list here. Let's examine here. Head is pointing to this node with data element 1. Previous is pointing to node with data element 1, 2. Also tail. Okay. But this node with data element 2 is pointing to null, but no one is pointing to it. Tail is not pointing to it. Head is not pointing to it. Previous is not pointing to it. Okay. Although current is pointing to it. Current is pointing to it, but current is only a temporary node. Current is only a temporary node, including previous. Once we go out of this method, both current and previous will be garbage collected because it is not part of our constructor. Our constructor only instantiates head and tail. This head and tail will be retained, but previous and current will not be retained because once we go out of our removeLast, they are going to be garbage collected, current and previous. Okay, so the final loop, so this will be deleted since no one is pointing to it. This will be garbage collected also, including current will be garbage collected. Current will also be garbage collected. So the final loop of our linked list is this. Okay. Let's examine the complexity of this code. So return null 1, 1, 1. This is n, right? Because it's a while loop. 1, 1, 1, 1. Final complexity of this removeLast is order of n. Finally, we have remove operation. We have already discussed removeFirst and removeLast, but what about if I would want to remove at the middle of my list? So this code will be removing a node based on the parameter object. So if that object is present on the linked list, then that node containing that object will be deleted or removed. Okay, so my code is node current is equal to head, previous is equal to null. So these are temporary nodes being created. And then while current is not equal to null, I would like to issue this condition. If comparable E, current.data is typecasted to comparable E, and then that compared to object is equal to 0. This means that if the object the value of the object is equal to the value of the current.data. If that is equal to 0, then it is true. If it's equal to other value than 0, then it is false. Okay? So within that condition, there is another condition. Current is equal to head, return removeFirst. And then if current is equal to tail, return removeLast. Still within the condition, current size minus minus, previous.next is equal to current.next, return current.data. Okay? If this condition is satisfied, so still within the while loop, previous is equal to current, current is equal to current.next, and that outside the while loop, I have return null. Okay? Let's examine the code. If linked list is empty, I have this code for my tester class. List I, integer list, is equal to new linked list integer. List.remove 1. Okay? List.remove 1. So this is the graphical representation. The instantiation of my list object will trigger this head and tail node pointers pointing to null, and then we will try to do now our remove with 1 being passed, with the value 1 being passed to our object. It's an integer type, so this e will become integer. So there we're going to instantiate our current and previous node, temporary nodes. So the graphical representation is like this. All of the 4 will be pointing to null. Okay? While current is not equal to null, current is pointing to null. So this is false. We're going to go outside the loop and we are going to return null. So step number 9, get out of the function and return null. So that's for our empty linked list. What about if we are going to remove at the intermediate of the linked list? If we're going to remove at the middle or within the linked list, I have a code for my tester class like this. Int x is equal to 4. And I have a for loop. Int I is equal to 0. If I is less than x, I plus plus. Then this is my statement. List.addFirst I. Then I have list.remove with parameter value of 2. So this is the graphical representation. So this code, line of code, from int x is equal to 4 until the end of my for loop will trigger this graphical representation. I have my head pointing to node with data element 3. Okay, this is addFirst, so meaning from 0 to 3, 3 will be the first data element in my node. So that's descending. So 3, 2, 1. Okay. And then head is pointing to my node with data element 0 and node.next is pointing to node. Okay. So we're going to examine now a remove method in our function remove. Okay. So 2 is passed here. E will become an integer and our object is equal to 2. So number 1 step is current will be pointing to head. Head is pointing to this node, so current will be pointing to this node also. And then previous is equal to null, so this is it. Let's go to our while loop. While current is not equal to null, current is not equal to null, null is here. So my while loop will loop until here. My while loop, my current is still here. Okay, but within my while loop, I have a condition. So we will not be traversing through our linked list until we reach the null here if our condition should be satisfied. So okay, let's go to our condition. If current.data, which is 3, equal to object, which is 2, then do this. Then do step 2 until step 6. But since it's false, we're going to go to our step 7. Previous is equal to current. Previous is equal to current. So current is pointing to this node, then previous will be pointing also to this node. And then step number 8, current is equal to current.next. So current.next is pointing to this node. So my current now will be pointing to this node. So the final graphical representation until step 8 is this. Previous is pointing to this node. Current is pointing to this node. Okay. That's the first iteration of my while loop. So we're going to test again the condition. Current is not equal to null. So current is not equal to null because it's still equal to node with data element 2. So we're going to go again here, second iteration of our loop, and we're going to compare current.data. Current.data is 2, and our object value is 2. So is 2 equal to 2, then it's true. We're going to do the statements within our if statement. Okay, now let's test first if current is equal to head. Is current equal to head? Head is pointing to this one, so it's false. If current is equal to tail, current is here, tail is pointing to this node. Tail is pointing to this node. Okay, so it's false. So let's get out there. Current size minus minus. So current size from 4 it will become 3, and then previous.next is equal to current.next. Previous.next will be equal to this one. Current.next is pointing to this node, so our previous.next will now be pointing to this node with data element 1. So it's depicted here. Previous.next will be pointing to this node with data element 1. Okay, and then return current.data. Return current.data. We're going to return the value of current data, which is 2, and then we're going to go outside our function. So this, let's examine the final, let's examine the loop of our linked list after returning the current.data. So my linked list head is pointing to node with data element 3. Previous is pointing to what this head is pointing to. My node.next with data element 3 is pointing to this node with data element 1. And then node.next pointing to this node with data element 0. Node.next pointing to null. Now my node with data element 2, which current is pointing to, its node.next is still pointing to node with data element 1. But once our compiler and our Java virtual machine assesses our linked list, node current, which is a temporary node, will be garbage collected. Previous, which is a temporary node, will be garbage collected too. So this node with data element 2 is pointing to this node, but no one is pointing to this node already. Hence, will also be garbage collected. Okay? So the final look of our linked list is like this. Okay? This is the final look of our linked list. So there are other operations of our linked list, but I believe that I've discussed and demonstrated the basic operations. The other operations that are included in your learning tasks, like contains, pick first, pick last, I will leave it for you to understand, because pretty much it's simple to understand. Okay, so finally, let's try to simulate using our tester class. Okay, our main method. So if I have a instantiated list object with an integer parameter, with an integer data type parameter, and then I have int n is equal to 5, I would like to look and do my list that add first, and then my I will be the value of, will be the parameter value of that add first, and then I would also like to add last through loop. Then I want to remove first, I want to remove last, I want to remove a node with a data element, I want to remove a node with a data element of 3 if there is. And then I want to system.out.println list that contains 3, system.out.println list that pick first, and then system.out.println list that pick last. What will be the output in my console? So the output in my console will be, of course, I have this kind of lines of code that will print to my console. So the contains method will return either true or false. So if 3 is seen on my linked list, the data element of the nodes in my linked list, then it will return true. Else, it will return false. So 3 is present, true. And then pick first, 2, pick last, 3. So this is the graphical representation, the final one. Okay. So head is pointing to node with data element 2, and then there, tail is pointing to node with data element 3, node that next is pointing to none. Okay.